Problem B2. Bello College has a homemade 500 kilovolt 1D graph proton accelerator, designed and constructed by the students and the faculty. Accelerator DOOM, assume it is a sphere, accelerating column, bending electromagnet, the accelerator dome, an aluminum sphere of radius A equal 0.5 meters, is charged by a rubber belt with the width W equal 10 centimeters that moves with the speed Vb equal 20 meters per second. The accelerating column consists of 20 metal rings separated by glass rings. The rings are connected in series with the 500 megaohm resistors. The proton beam has a current of 25 microampere and is accelerated through 500 kilovolt and then passes through a tuning electromagnet. The electromagnet consists of a wound copper pipe as a conductor. The electromagnet effectively creates a uniform field B inside a circular region of radius B equal 10 centimeters and 0 outside that region. On the figure, DOOM metal rings of accelerating column, glass separators, electromagnet target resistor chain, only 6 of the 20 metals rings and resistors are shown in the figure. The fuzzy gray path is the path taken by the protons as they are accelerated from the DOOM through the electromagnet into the target. Question A. Assuming the DOOM is charged to 500 kV, determine the strength of the electric field at the surface of the DOOM. Solution for question A. Potential for this sphere equal this expression. Electric field near the surface of the sphere equal this expression. It means that the electric field near the sphere equal V over A, which is 10 power 6 volt per meter. That's the answer for question A. Question B. Assuming the proton beam is off, determine the time constant for the accelerating DOOM, the time it takes for the charge on the DOOM to decrease to 1 over E, which is approximately equal 1/3 of the initial value. Solution for question B. Solution for question B. Time constant for capacitor connected in series with the resistor equal to RC, where R is resistance for all of these resistors connected in series, and C is capacitance for sphere, which is equal to 4 pi epsilon 0 A. When we put all numbers, we will get for capacitance this amount. For total resistance for 20 resistors, we have 10 power 10 ohm, and finally time tau to discharge our capacitors in proportion 1 over E. We have tau equal this amount. So that's the answer for question B. Question C. Assuming the 25 microampere proton beam is on, determine the surface charge density that must be sprayed onto the charging belt in order to maintain a steady charge of 500 kV on the DOOM. Solution for question C. There are two main ways to discharge this sphere. One is a proton beam, which is 25 microampere, and other is through resistors. which we can use just Ohm law. That will be V over R, which is 50 microampere, and total current will be 75 microampere. And this current we have to produce using this charged belt. It means that we can find what is the surface charge density for this belt. We have a total current equal delta Q over delta T, and delta Q equal just a sigma multiplied by delta A over delta T, where delta A is how fast is this area moving, and area moving with the speed VB multiplied by width of this belt. And from this formula we can find what is sigma. So finally we have sigma equal current I over VB multiplied by W, where VB that's the speed of this belt and W is the width of this belt, and the answer is 37.5 microcoulomb per square meter. That's the answer for question C. Question D. The proton beam enters the electromagnet and is deflected by an angle theta equal 10 degrees. Determine the magnetic field strength. Basically, to solve this problem, we need to calculate what is the radius of this curve, because that's the radius of proton beams in a constant magnetic field. And we can count what is the speed of this beam, and if we know what is radius of this arc, we can count what is the magnetic field. Let's do this. First of all, protons, they are not relativistic, and we can find what is the speed using acceleration by voltage 500 kilovolt. So we have kinetic energy for protons equal QV. When it moves in a magnetic field, we have other expression. Combining both expressions, we can find what is magnetic field B. So last step is to find what is the radius of this arc, and we can do it using some geometry. Because this arc crossing this circle on the right angle, we can draw this two radii for this arc, and from this geometry we can find that tangent theta over 2 equal B over R. And now we can put R from this formula in this expression for magnetic field and find that it's equal to this expression, which is approximately 0.0894 Tesla. That's the answer for question D. Question E. The electromagnet is composed of layers of spiral wound Cooper pipe. The pipe has inner diameter di equal 0.4 centimeters and the outer diameter d0 equal 0.5 centimeters. The copper pipe is wound into this flat spiral that has an inner diameter di equal 20 centimeters and the outer diameter d0 equal 50 centimeters. Assuming the pipe almost touches in the spiral winding, determine the length L in one spiral. Solution for question E. We can treat this question as not in 3D but in 2D. We can find what is area of this spiral and equalize it to area of the pipe. So we have from one hand this area equal pi over 4 multiplied by d0 square minus di square, and from other hand we have area equal length of spiral multiplied by outer diameter of this pipe. From here we can find what is L. And finally we have length of spiral L equal 33 meters. That was the answer for question E. Question F. Hollow pipe is used instead of solid conductors in order to allow for cooling of the magnet. If the resistivity of copper is ρ equal 1.7 by 10 power negative 8 ohm by meter, determine the electrical resistance of one spiral. Solution for question F. We can use a formula for resistance using resistivity, length, and cross-sectional area. That will be this expression, and after putting numbers we have 0.079 ohm. That was solution for question F. Question G. There are n equal 24 coils stacked on top of each other. Tap water with an initial temperature of Tc equal 18 degrees Celsius enters the spiral through the copper pipe to keep it from overheating. The water exists at a temperature of Th equal 31 degrees Celsius. The copper pipe carries a direct 45 ampere current in order to generate the necessary magnetic field. At what rate must the cooling water flow be provided to the electromagnet? Express your answer in liters per second with only one significant digit. The specific heat capacity of water is 4200 joules per 1 degrees Celsius per kilogram. The density of water is 1000 kg per cubic meter. Solution for question G. First, we can write rate of heat generated in these coils, which is I square R, and R equal number of coils multiplied by resistance of one spiral, which we already counted. Total power created in this stack of coil equal 3840 watt. This dissipated power must be equal to heat capacity for water multiplied by temperature difference, which is 31 minus 18, multiplied by density of water and multiplied by flow rate in liters per second. And now we can count this rate. That will be approximately 0.07 liters per second if we round it to the first digit. That was answer for question G. Question H. The protons are fired at a target consisting of fluorine atoms, Z equal 9. What is the distance of closest approach to the center of the fluorine nucleus for the protons? You can assume that the fluorine does not move. Solution. Conservation of energy for this process will give us that total kinetic energy of proton, which is QV, equal to energy of interaction between proton and the target atom, which is Z Q square over 4 pi epsilon 0 R. And from here we can find what is closest approach R. That will be approximately 2.59 by 10 power negative 14 meters. That's the answer for last question H.